Today we're going to be looking at another one of Practical Engineering's videos. Specifically, how would a nuclear EMP affect the power grid? Where I worked at, we actually had procedures for grid instability events. For those of you who don't know me, I'm Tyler Foltz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Check it out.
A nuclear detonation is unwelcome in nearly every circumstance.
That's got to be quite the big understatement. Unless you're testing it, but I guess that one's on you.
These events are inherently dangerous, and the physics of a blast go way beyond our intuitions. That's especially true in the upper atmosphere, where the detonation interacts with Earth's magnetic field and it
talks about going beyond our intuitions. That's a very interesting point in that a lot of times their effects are somewhat exaggerated, mainly when it comes to how much radiation is released and how much of it actually hits the surface. Because after all, radiation, we can't see it. It's this scary thing that we're not sure about. Yeah, beyond our intuition. I haven't heard that exact phrasing, but I get it.
Its atmosphere in some very unique ways to create an electromagnetic pulse. An EMP actually has three distinct components, all formed by different physical mechanisms that can have significantly different impacts here on Earth's surface. The first part of an EMP is called E1. This is the extremely fast and intense pulse that immediately follows detonation. The gamma rays released during any nuclear detonation collide with electrons, ionizing atoms and creating a burst of electromagnetic radiation. And
not just gamma rays, but also neutrons, fission fragments. I mean, predominantly gammas are going to have the most range, so they're going to have the most widespread effect, but there's all kinds of radioactive bits and pieces coming out of a nuclear explosion. And he was right that it's fast. It can happen on the order of nanoseconds, which is comparable to the speed of the nuclear reactions inside of the bomb itself. There's even a unit of time for nuclear explosions. It's called the shake. A shake is 100 nanoseconds, like a few shakes of a rabbit's tail, or something like that. I don't actually know. It was another weird unit that came out of the Manhattan Project because all of it was sworn to secrecy. Also, anything to not use the metric system, apparently.
Generally bad on its own, but when detonated high in the atmosphere, Earth's magnetic field interacts with those free electrons to produce a significantly stronger electromagnetic pulse than if detonated within the denser air at lower altitudes.
It's an interesting parallel.
E1 pulse comes and goes within a few nanoseconds, and the energy is somewhat jokingly referred to as DC to daylight, meaning it's spread across a huge part of the electromagnetic spectrum.
That's an interesting way to put that. I haven't actually heard DC to daylight, but it's interesting that the parallels between the higher the altitude, actually the less risky of the fallout, because a lot of it is just going to be blown away up into the upper atmosphere, some of it out into space, though a lot of the heavier stuff will fall back to Earth, but it's going to be widespread and diffuse, less concentrated, less of a chance of a lethal dose compared to a surface detonation. Now, not to say there's not going to be any acute radiation poisoning from a nuclear attack. Obviously, there is. But it's not as much compared to the effects of one detonated near the surface. So that goes down. But the effects of the EMP go up because you're closer to the magnetic field, and plus you have more line of sight to work with going down towards the Earth. Kind of like the explosion is worse for an airburst. Not a high altitude thing like he's talking about right here, but the fireball and the pressure shockwave are so much worse in an airburst, which is why that's mainly the preferred method for attacking, say, a non-hardened target. So not like a bunker or something that you actually want to detonate on the surface or even subsurface. So it's this interesting sliding scale of maximize your dose on the ground, less dose, whereas on the ground, radiation can be the deadliest compared to the other ones. An air burst, where the shockwave and the fireball is the worst. And then the super upper atmosphere one, where the main hazard is going to be the EMP.
The E1 pulse generally reaches anywhere within a line of sight of the detonation, and for a high-altitude burst, this can cover an enormous area of land. At the height of the Yucca test, that's a circle with an area larger than Texas. A weapon at 200 kilometers in altitude could...
I'm really liking Grady's voice here. Very calm, explaining about crazy, deadly stuff. Kind of like when you have people like Nile Red or Styropyro doing crazy experiments. It shows a certain level of professionalism, and like you're kind of used to this sort of stuff. It's good. It's something that is clearly trained.
Impact a significant fraction of North America, but not everywhere within that circle experiences the strongest fields. In general, the further from the blast you are, the lower the amplitude of the EMP.
Just like you see with the destructive forces of a nuclear explosion, say an airburst or a ground burst, not everything in this circle is gone. That's another misconception out there that I'm glad he's pointing out here. Not even the EMP isn't going to kill every electrical component, every grid component within this big dotted line here.
But because of Earth's magnetic field, the maximum amplitude occurs a little bit south of ground zero in the northern hemisphere, creating this pattern called a smile diagram. But no one will be smiling to find out that they're within the affected area of a high-altitude nuclear blast. Although a weapon like this wouldn't damage buildings, create nuclear fallout, be felt by humans, or probably even visible to most, that E1 pulse can have a huge effect on electronic devices.
In some cases, it could be worse if it affects a wider area and people are ill-prepared to handle the EMP. And frying a bunch of electronics, depending on what it is, can be just as deadly. Suddenly disabling critical infrastructure for, say, hospitals, and for nuclear power plants. If a nuclear power plant suddenly loses the off-site power, its connection to the grid, the reactor will automatically shut itself down and place itself in a safe condition. And then all of the safety systems, in order to keep the core cooled, because remember, nuclear reactors produce decay heat even after they are shut down. But all of those cooling pumps can be powered by standby diesel generators, which are located within structures, so they should be okay. Barring a direct hit, though. A direct hit to a nuclear power plant with a nuclear weapon, keeping the nuclear power plant safe is probably the least of your concerns at that point, but... Anyway, nuclear power plants can be maintained safe. And there's also special procedures for grid instability, which say the nuclear power plant is further away. It doesn't directly disable the transformers at the plant, but it affects enough of the grid that the grid has to start load shedding. Then the power plant could shift a lot of its loads to alternative power supplies. Even cross-connecting, say it's a site with multiple reactors, even cross-connecting the reactor's loads to each other in certain extreme circumstances. But that would be a scenario where you're able to keep the reactors running in the event of an event like this.
Probably familiar with antennas that convert radio signals into voltage and current within a conductor. Well, for a strong enough pulse spread across a huge range of frequencies, essentially any metallic object will act like an antenna, converting the pulse into massive voltage spikes that can overwhelm digital devices. And the E1 pulse...
Digital, sensitive electronics, satellites, those will be a lot more vulnerable than even the grid to these sort of pulses.
Happens so quickly that even devices meant to protect against surges may not be effective.
Yeah.
Of course, with just about everything having embedded electronics these days, this has far-reaching implications. But on the grid, there are really only a few places where an E1 pulse is a major concern. The first is with the control systems within power plants themselves. The second is communication systems.
Now, the control systems, one of the good things about nuclear plants is a lot of their switches and internal systems are so old. A lot of these newer, fast responsive controls that are more vulnerable aren't as widely used, so I guess that's one odd advantage to them, kind of a similar reason that nuclear power plants are harder to hack, because you can't really hack a computer that runs on vacuum tubes. I'm just kidding, they don't actually run on vacuum tubes, but they do use a lot older software, even those old-timey orange plasma screens that you use to monitor certain critical parameters. And we've run drills on not on a nuclear EMP specifically, but on grid disruption events and certain loss of certain power supplies events. And there's so many backup systems built into the control room of a nuclear power plant that you could lose just about anything. And one, the system will shut itself down. And two, you'll have all your strings of backup systems to supply critical cooling long after the reactor is shut down. And additional ones can be brought in from outside the range of the EMP. There are satellite locations within the US that could bring in additional diesel generators, transformers, power supplies, by helicopter if necessary. That sort of stuff was put in after Fukushima, when you can see how vulnerable certain systems are to loss of power. So even more backup power.
It's used to monitor and record data to assist grid operators. The EPRI report focused primarily on the third hazard associated with an E1 pulse, digital protective relays. Most folks have seen the breakers that protect circuits in your house. The electrical grid has similar equipment used to protect transmission lines and transformers in the event of a short circuit or fault. But unlike the breakers in your house that do both the sensing for trouble and the circuit breaking all in one device, those roles are separate on the grid. The physical disconnecting of a circuit under load is done by large, motor-controlled contactors quenched in oil or dielectric gas to prevent the formation of arcs. And the devices that monitor...
And that's just because you're dealing with such extreme voltage compared to what you're dealing with around the house. The substation where I worked at was 345,000 volts.
Monitor voltage and current for problems and tell the breakers when to fire are called relays. They're normally located in a small building in a substation to protect them from weather.
Some big relays.
That's because most relays these days are digital equipment, full of circuit boards, screens, and microelectronics.
True, but they're also mechanical backups that fail safe. They fail in the open position, meaning the breaker is open and this faulted, affected portion of the grid is isolating, preventing a cascading grid failure, which would be horrible. So they do at least have mechanical backups when the electrical or the sensitive equipment does fail. Same is true for a lot of equipment in nuclear power plants. They fail in the safe condition. Safe meaning that's why the reactor shuts itself down when you lose off-site power. And everything with core cooling during either loss of electrical power or loss of instrument air, in the case of an air-operated valve, would fail to full cooling, which when you're shut down is a good spot to be in if you're going to have a piece of equipment fail on you.
And all those components are particularly susceptible to electromagnetic interference. In fact, most
except for the mechanical
have strict
ones.
regulations about the strength and frequency of electromagnetic radiation you can foist upon the airwaves. Rules that I hope I'm not breaking with this device. This is a pulse generator I bought off eBay just to demonstrate the weird effects that electromagnetic radiation can have on electronics. It just outputs a 50 megahertz wave through this antenna, and you can see when I turn it on near this cheap multimeter, it has some strange effects. The reading on the display gets erratic, and sometimes I can get the backlight to turn on. You can also see the two different types of E1 vulnerabilities here. An EMP can couple to the wires that serve.
Never underestimate the power of twirly electrical thingies. I don't know, I'm not an electrician.
As inputs to the device, and an EMP can radiate the equipment directly. In both cases, this little device wasn't strong enough to cause permanent damage to the electronics, but hopefully it helps you imagine what's possible when high-strength fields are applied to sensitive electronic devices. The EPRI report actually subjected digital relays to strong EMPs to see what the effects would be. They used a Marx generator, which is a voltage multiplying circuit, so I decided to try it myself.
Oh, if you want to see me react to a crazy homemade Marx generator, I did a reaction video to one of Electroboom's videos on that exact subject, and there were a lot further discussions about electrical safety in that video. I'll pin it down below if you want to see it.
A Marx generator stores electricity in these capacitors as they charge in parallel.
Steps it all the way
when
up.
Triggered, the spark gaps connect all the capacitors in series to generate very high voltages, upwards of 80 or 90 kilovolts in my case.
That is an oh look, there's Electroboom right there. That is an extremely high voltage for something just lying around the house. In fact, the output voltage of the main generator transformer was, at the nuclear plant I worked at, was a mere 25,000 volts. And of course, that gets stepped up to 345,000 volts in order to distribute it to over hundreds of miles to cities. After all, higher voltage, less losses in your transmission line.
My fellow YouTube engineer, Electroboom, has built one of these on his channel if you want to learn more about them.
There we go.
That's the video I was talking about.
Mine generates a high voltage spark when triggered by the screwdriver. Don't try this at home, by the way.
Nope.
I didn't design an antenna to convert this high voltage pulse into
going to fry his
EMP,
iPad?
but I did try a direct injection test. This cheap digital picture frame didn't stand a chance.
Oh, digital picture frame.
Just to clarify, this is in no way a scientific test. It's just a fun demonstration to give you an idea of what an E1 pulse might be capable of.
Yeah. Prompt, very fast increase in your electric field strength, then yeah, a Marx generator is not a bad way to at least illustrate that principle without having to test your own high-altitude nuclear weapon.
The E2 pulse is slower than E1 because it's generated in a totally different way, this time from the interaction of gamma rays and neutrons. It turns out that an E2 pulse is roughly comparable to a lightning strike. In fact, many lightning strikes are more powerful than those that could be generated by high-altitude nuclear detonations.
I've also heard the phases, in addition to E1, E2, and E3, I've heard the prompt EMP for E1, the intermediate EMP for E2, and then E3 being the late one. But yeah, just like lightning, the residual gamma rays interacting with it, because you're going to have some later parts of that nuclear reaction. The delayed neutrons would start to show up from the fission, but in a nuclear bomb, you're not going to have that many delayed neutrons because the goal is for it to be prompt critical. So a lot of those neutrons had their fissions. We're talking E1 time frame, or even before that, like on the order of 10 to the minus 15 seconds. So you might as well consider those neutrons creating that reaction so quickly to be instantaneous, even compared to the speed of an E1 pulse.
Of course, the grid's not entirely immune to lightning, but we do use lots of lightning protection technology. Most equipment on the grid is already hardened against some high voltage pulses, such that lightning strikes don't usually create much damage.
I've seen a lightning strike hit the substation where I worked at. Yeah, it triggered a few alarms. The grid operator sent a few technicians out to verify, but it didn't really do much. We saw it. You could see it in the control room meters on grid frequency, having a small effect there, and driving a few of the plant's inverter alarms, because after all, everything is downstream of the grid. Those were inverters that would eventually be connected to the grid. They were in that same electric flow path, as opposed to the plant's critical inverters, which have separate on-site vital power supplies that could be completely independent from the grid. So critical parameters like reactor coolant, temperature, and pressure aren't subject to the whims of the grid in terms of indication. Keep in mind, none of these would affect the actual reactor.
So the E2 pulse isn't as threatening to our power infrastructure, especially compared to E1 and E3. The final component of an EMP, called E3, is again much different than the other two. It's really not even a pulse at all because it's generated in an entirely different way. When a nuclear detonation happens in the upper atmosphere, Earth's magnetic field is disturbed and distorted.
And keep in mind the time frame here. Here we're getting into the order of seconds to minutes. These other two pulses were so fast that the explosion hasn't even happened yet. The reaction did. The reaction was ancient history, and then I guess you could say classical history was the E1 pulse, and medieval history was the E2 pulse, and now we're getting into the more of the spots you can actually see.
As the blast dissipates, the magnetic field slowly returns to its original state over the course of a few minutes. This is similar to what happens when a geomagnetic storm on the sun disrupts Earth's gravity, and large solar events could potentially be a bigger threat than a nuclear EMP to the grid.
The difference is you'd be able to see them coming. It was like the nuclear EMP, well, I guess you could see the missile or the bomb or whatever device in transit and then prepare for them. But this one would cause a much more widespread area, but you could do things like turn off certain power supplies in the grid so you don't lose the entire grid. You basically do a controlled planned shutdown so it's easier to turn everything back on. Whereas right after the explosion happens, you don't have a warning.
In both cases, it's because of the disturbance and movement of Earth's magnetic field. You probably know what happens when you move a magnetic field through a conductor. You generate a current. We call that coupling, and it's essentially how antennas work. And in fact, antennas work best when their size matches the size of the electromagnetic waves. For example, AM radio uses frequencies down to 540 kilohertz. That corresponds to wavelengths that can be upwards of 1,800 feet or 550 meters. Big waves, rather than serving as a place to mount.
And keep in mind, all this is considered radiation. Electromagnetic radiation, non-ionizing, but with that whole adage you hear about radios or cell phones, I've heard it more with cell phones, causing radiation. Yes, it does, just not the ionizing kind. So no, holding a phone up to your ear isn't gonna cause cancer any more than anything else anyway.
Antennas like FM radio or cell towers, AM radio towers are the antenna. The entire metal structure is energized. You can often tell an AM tower by looking at the bottom because they sit atop a small ceramic insulator that electrically separates them from the ground. As you can imagine, the longer the wavelength, the larger an antenna has to be to couple well with the electromagnetic radiation. And hopefully you see what I'm getting at. Electrical transmission and distribution lines often run for miles, making them the ideal place for an E3 pulse to couple and generate current. Here's why that's a problem. All along the grid, we use transformers to change the voltage of electricity. On the transmission side, we increase the voltage to reduce losses in the lines, and on the distribution side, we lower the voltage back down to make it safer for customers to use in their houses and buildings.
Yeah, have fun plugging your toaster into 345,000 volts.
Those transformers work using electromagnetic fields. One coil of wire generates a magnetic field that passes through a core to induce current to flow through an adjacent coil. In fact, the main reason we use alternating current on the grid is because it allows us to use these really simple devices to step voltage up or down. Up to a certain point, most materials used for transformer cores have a linear relationship between how much current flows and the strength of the resulting magnetic field. But this relationship breaks down at the saturation point, beyond which additional current won't create much further magnetism to drive current on the secondary winding. An E3 pulse can induce a roughly DC flow of current through the transmission lines. So you have DC on top of AC, which creates a bias in the sine wave. If there's too much DC current, the transformer core might saturate when current moves in one direction but not the other, distorting the output waveform. That can lead to hot spots in the transformer core, damage to devices connected to the grid that expect a nice sinusoidal voltage pattern, and lots of other funky stuff.
And this, remember, this one lasts longer, so it has just that greater probability of doing something compared to, say, the E1 or the E2. So there's more probability of this causing something just because it's longer, even though the electric field strength is significantly weaker than an E1.
So what are the implications of all this? For the E1 pulse damaging some relays, that's probably not a big deal. There are often redundant paths for current to flow in the transmission system. That's why it's called the grid. But the more equipment that goes offline and the greater the stress on the remaining lines, the greater the likelihood of a cascading failure or total collapse.
Yeah, so the grid, one key component of the grid is it needs to maintain a certain frequency in order for basically all the homes and whatever uses the grid as its source of power to rely on. In the US, it's 60 hertz. And a standard frequency is why so many devices are designed the way they are. And if something were to change that, like you suddenly have a whole bunch of units, whether they're nuclear or fossil or even wind and solar, though in the case of the latter, it's less of an impact, suddenly start tripping off, the grid kind of loses its ability to maintain that. And if it loses its ability to maintain that frequency, well, that's an emergency shutdown before everything starts to break. Basically any sort of generator or transformer that's on the grid. A few years ago in Texas, there was a freeze, or a lot of power plants, especially wind turbines, were shut down. And there were moments in time where the grid was on the order of 5 minutes out from having to shut down and do a black start, which is starting from completely de-energized. And that would take a while. So during that freeze event, whereas a lot of people were without power for a few days, maybe a week, I don't exactly remember, this could have brought it up to several weeks to months, because it's a very coordinated and concentrated effort. It has to be done in sync in some cases, hence, to maintain that frequency. It's a very controlled startup. Maintaining grid frequency is a bit like maintaining tempo in a musical performance, and the conductor, pun intended, and that would be both the grid operator and the power plant operators, the control room operators, when syncing a generator to the grid, need to ensure everything is done in sync.
EPRI did tests simulating a 1 megaton bomb detonated at 200 kilometers in altitude. They estimated that about 5% of transmission...
Average nuclear weapons are on the order of 400-ish kilotons. Several of which are a good bit smaller, but 1 megaton's pretty sizable. We're a good bit away from the era of massive nuclear weapons like the Castle Bravo device or the Tsar Bomba that was 50 megatons. So 1 megaton high altitude is pretty big.
Lines could have a relay that gets damaged or disrupted by the resulting EMP. That alone probably isn't enough to cause a large-scale blackout of the power grid, but don't forget about E3. EPRI found that the third part of an EMP could lead to regional blackouts encompassing multiple states because of transformer core saturation and imbalances between supply and demand of electricity.
And you'll see those in things like substations and switchyards, more so than probably any other component.
Their modeling didn't lead to widespread damage to the actual transformers, and that's a good thing because power transformers are large, expensive devices that are hard to replace, and most utilities don't keep many spares sitting around.
Yep, I've seen a few main transformer replacements in my career, and that is quite the outage project. Obviously, you'd only replace something like that when the nuclear power plant is shut down.
All that being said, their report isn't without criticism, and many believe that an EMP could result in far more damage to electric power infrastructure. When you combine the effects of the E1 pulse and the E3 pulse, it's not hard to imagine how the grid could be seriously disabled. It's also easy to see how even if the real damages to equipment aren't that significant, the widespread nature of an EMP, plus its potential impacts on other systems like computers and telecommunications, has the potential to frustrate the process of getting things back online.
I was going to say there could be even more of to sensitive stuff like computer, even things that you don't think of as critical infrastructure. You take out, I don't know, the New York Stock Exchange or something like that. That's going to cause all kinds of panic, and there's all these secondary effects that aren't just the equipment being affected that you see. The amount of panic from losing power can be more damaging than what sort of equipment was actually damaged in the event. Mentioned people on life support in hospitals. Granted, they should have backup diesels, but still, those have a finite fuel supply, and you have to bring in additional fuel trucks depending on how long this outage is supposed to be. It can get quite chaotic that quickly, even if this clearly isn't going to be some sort of apocalyptic type scenario. It's also not good for any aircraft that happen to be in the area.
A multi-day, multi-week, or even multi-month blackout isn't out of the question in the worst-case scenario. It's probably not going to cause a Hollywood-style return to the Stone Age for humanity.
What about multi-month? I mean, worst-case scenario, okay, if this happens in the middle of a nuclear war, then maybe, because if a lot of emergency grid responders are going to be somewhat preoccupied. But you mentioned worst-case scenario, I guess you can get there, or like the solar storm event that for whatever reason nobody decides to make any adjustments, or we don't see it coming for whatever reason, that could potentially be more devastating.
But it is certainly capable of causing a major disruption to our daily lives.
I like this channel. I like his calm demeanor and how he's not overly alarmist. He kind of shows a bit of both sides. As far as where I stand on this, there's a lot. I remember seeing a lot of crazy video games out there saying, ooh, one nuclear EMP wipes out all of North America to set up some sort of crazy Red Dawn style invasion. No, that's wrong for a whole mess of reasons. It's another one of those things that we can prepare for. Grid operators any sort of grid instability events can be prepared for. If it's solar activity, that can be prepared for with proper forecasting and operations procedures for the grid operators and for power plant operators, including nuclear plants. As far as weaponizing this, it's very imprecise, so I'm not a weapons expert, but generally people like them to be a bit more reliable and produce somewhat more sustainable results, considering this sort of thing could be affected by weather, whether it be earth weather or solar weather, and have a whole bunch of unintended consequences even for the aggressor in this case. Like if they happen to be in a country that's bordering the country that's the target, they could do more damage to their own country that way. Anyway, like always, I think all those extreme apocalyptic scenarios are super exaggerated. Thank you very much for watching. I'll see you next time.